Hello guys, welcome to my new video for M.sc Mathematics. So in the last video, I have given you the notes which are required to understand the question answer for topology, and I have also started giving you question answer for topology. So this session will be totally based on question answers for topology. Okay, now let's start. Okay, before start, I want to let you know that if you have not gone through my previous videos, then whatever question answer I will be giving you in this video, that will be quite difficult for you to understand. Okay, but if you have gone through all of my previous videos, then everything will be very easy to understand for you, whatever I will be giving in this video. Okay, let's start. Find the first question. Find the interior, exterior, and boundary of a set E if x is equals to a b c d e, t is equals to x is the main set. Okay, x is the main set, t is the topology, and e is the set for which we have to find out the interior point, exterior point, and boundary. Okay, so just go through the question for a minute. Okay, so I think you have gone through this question. Take a screenshot of the page, right? Because if you want to make a good note for topology, so whatever video I am giving, take the screenshot of each page and take a printout of all of this and then pin up those in sequence. It will become a very good note for you as far as topology subject is concerned. Okay, so find the interior, exterior, and boundary of set E. So it is given that X is A, B, C, D, E is the main set. T is the topology. So topology has the class of subsets like phi X, A, C, D, A, C, D, B, C, D, E. Okay, and B, C, D is the set for which we have to find out interior, exterior, point, and boundary. So what is basically interior of a set, or interior point of a set, or we can say interior of a set? Okay, what is interior point of a set and interior of a set? Let's see. Let Xt be a topological space and E is a subset of X and P be a point such that P belongs to E. Okay, then P is interior point of E if there exists some open set G belongs to T such that P belongs to G and G belongs to P belongs to G and G is a subset of E. Okay, P belongs to G and G is a subset of E. This is very important point. P belongs to G and G is a subset of E. Then we say that the interior point or the interior point of a set, let's suppose this is interior point, so interior may be the whole region. Okay, so interior may be the whole region. Okay, this may be interior point, interior may be the whole region. So we say, and it may contain many more. It is not only one point. Okay, interior, I mean the point will be interior point, this point will be interior point. Okay, within the interior, whatever point lies will be called interior point. So we denote it like this. Interior of X will be the union of all the open set G. Okay, all the open set G which will be the subset of E. Okay, union will be the interior point will be the union of all open set G which are the subset of E. Okay, now let us what is given in the question. This is the main set, this is the topology, and this is the set of which we have to find out the interior, exterior, and boundary. So start with the B point of the start with the B point, I mean B member B of the set E. Okay, we can see that open set A, B, C, D, E contains B, right? At first check that the open set BCDE contains B, right? So check BCDE. Okay, this set, it contains B, right? It contains B. But if you see, BCDE is not a subset of BCD, right? BCDE is not a subset of BCD. Yes, in the open set, in this open set, B point is contained. But what is the definition? Okay, that open set should be subset of E, right? Open set should be subset of E. Only then we can say the interior point, right? Else we cannot say the interior point. So here we can see that BCD is not a subset of E, right? So we can say from here, because this is the only set which contains B among all of these sets, all of the open sets, right? So we can say that B is not an interior point, right? B is not an interior point, okay, of E. B is not an interior point of E, okay. Now let's check with C, okay. If we see that ACD contains C point, BCDE contains C point, right? ACD content, everything is written here, okay? Everything is written here. That is why in the start of the video I have told you to take the screenshot of it, okay? So ACD contains C, BCDE contains C, and CD also contains C, right? But if you see that ACD, right? ACD is not a subset of BCD. Even BCD is not a subset of BCD, right? ACD is not a subset of BCD. BCD is not a subset of BCD, right? So we can ignore this. Let's check with this, okay? Let's check with CD. Now we can see that CD is a subset of BCD, right? CD is a subset of BCD, okay? So as per definition, what is happening? The open set G contains the point C, right? As well as the open set that contains the point C is a subset of E, right? So we can say C is an interior point of E. C is an interior point of E. Similarly, if we check for D, what we will see? For D, if we check B, C, D, E, this set contains D, this contains D, and this contains D, right? All of these three set contains D, but this set and this set not a subset of E, right? This set and this set not a subset of E, so we can ignore this. Now let us check this set. Yes, this set contains D, and as well as it is a subset of E, right? So as per definition, the open set, this is the open set that contains the point C and D, and this open set also subset of E, right? So we can say that C and D are the interior point of the set E, right? So we can say that interior point of set E are C and D. Let me adjust the paper. Okay, now so CD are the interior point. It is done. What are the interior point to be? We have found it. Now what is the exterior point of a set and exterior of a set? Let XT be a topological space E. Okay, let XT be a topological space. Okay, and E be any subset of X, then a point P belongs to X is said to be an exterior point of E if there exists an open set G such that P belongs to G belongs to the complement of E. Okay, P belongs to G. This subset should contain that point. Okay, but that Z should belongs to the complement of E, right? The complement of E. So for for more than one G we can say UG, right? Okay, maybe more than one open set can contain the exterior points, right? So we can union over there, like interior point. Here we can also actually uh, union. But if there is no exterior point, then we can say no exterior point exists. Okay. If there is no interior point, we can say no interior point exists. Okay. Let's see. For let okay, it is given that x is a b c d, t is phi x a c d s c d, and b c d e, and e is b c d. Now ec means elements other than b c d, right? What is the complement? Complement means the elements other than b c d. So here only a, right? Only a. If we check here, we will see that B, C, D, right? B, C, and D. This will be ignored because these are not the as far as complement of E is concerned. This belongs to E, so we have to remove this to find the complement of E, right? So what is left? E, A, and E left. What are left? A and E left. So in X, A and E are left. Okay. So if we check the open set G, we can see that A and E. If we check A and E, then we can see that there is no open set which is a subset of G, right? Like which is a subset. In the previous example, we see that how we find the interior point. Now if you come here, then you can see that A is the only subset. Okay, A is the only uh, okay. So what will be the set if we just ignore B C D? Then what we will have? We will only have like A and C. A and E. We will only have A and E, right? A and E. Now check which open set contain A, which open set contain E. Now if we check here that the set A only contain the point the point A. Also this is a subset of, we can say this is a subset. A is a subset of that set, is a subset of this set, right? Complement of E. A is a subset of complement of E. For other sets, this not contain E, this not contain E. Okay, this contain E, this contain E, but it is not a subset, right? It is not a subset. Even this contain A, but it is not a subset. Okay. So what we can say from here, that we will only consider A because this is the only subset. This is the only subset, or you can say it is the only open set. Okay, only open set which is the subset of complement of E, right? Which is the subset of complement of E. Okay. Again, I am going through. Okay, how we determine the complement of E? We just remove the member of the set from X which belongs to E. So we will be removing BCD. Then what will be left? A and E, right? So A and E left. Now we have to find that is there any open set which is subset of any of this member, which contains any of this member, and also subset of this particular set. What we have to find? We have to find the open set that will contain these 2 points, as well as that has to be a subset of this particular set, right? So we can see that only A is that open set which is containing the point A and also subset of this set AE, right? Rest of the sets are actually not subset, okay, of AE. None of the sets are subset of E except A, because EC, what is EC here? EC is equal to A, right? So as per definition, what we have to say? We have to find some point, right? We have to find some point. This will be, we have to find some point. which will be the subset of the complement, which will be the subset, which, I mean, we have to find that set which will be the subset of complement complement E, as well as that subset contains point which are the members of the complement of E, right? So we can see the only A is there, okay. Only open set A is there, which is a subset of A as well as it contain A, right? So we can say the exterior point is A. So we can say the exterior of the set is A. So the interior is CD, interior points of the set or interior is CD, exterior is A, okay. Now what is the boundary? Boundary of a set is the point, the set of points which does not contain either interior or exterior point, okay. Boundary of a set is those set of those points which does not contain either interior or exterior. So if we remove ACD, okay, this is the interior point and this is the interior points and this is the exterior point, right? So if we union interior exterior, we will get ACD, right? And then this, what is this? This is the union of interior and exterior, right? So if we just union interior exterior and remove that from X, what we will get? We will get B, we will get only B. So B will be the boundary of the set, okay. So B will be the boundary of the set. So I have told you that please go through my previous videos. If you have not gone through that, it will become difficult for you to understand, okay. But if you gone through my previous videos, this will become very easy for you to understand, okay. So the next question, what is the next question? Define open cover, sub cover and compactness of a set, okay. Open cover, sub cover and compactness of a set, okay. Go through the question for a few seconds, then I will be starting the answer. Okay, what is open cover of a set? A set subset of R here is real number, okay. A set subset of R and C. In the set we will learn from AI such that I belongs to I, okay. B collection of open set, okay. Then C is said to be open cover of S if let S belong, it is a subset of R and C is a open set which is represented like AI. I mean open set are the collection of subset, okay. Open sets are the collection of subsets like classes, okay, like class of a set, right? So that is why we are reading like this, that AI such that I belongs to I, be a collection of open sets, okay. Then C is said to be open cover of S if S is a subset of union of all these open sets, okay, all the open sets. C is the S is the subset of union of all the open sets, right? These are the open sets. These are the open sets. These are the open sets. Open sets, okay. Example, let S is a subset of real number and C equal to, and C is a set open interval. C is a collection of open sets. C is a collection of open sets which is like open interval minus n to n such that n belongs to n. Okay, n belongs to natural number. Then S will be the subset. S will be the subset of union of open interval of n and n, right? Open interval of n and n, and for every n belongs to n. Therefore, C open interval minus into n such that n belongs to n is open cover of R. Okay, is open cover of R. Now, what is subcover of a set? A sub collection of open cover of any set is called subcover. A sub collection of open cover of any set called a subcover. Example, if we have seen that this is a cover, then if we have this, we can say this is a subcover of C. Okay, you see it is started from minus 3n and 3n. It started from n minus n and n, so it will be a subcover. Both of this will be the cover of R. Okay, both of this will be the cover of open cover of R, but this will be the subcover of C, right? This will be the subcover of C. This both will be the open cover of R, but only this will be the subcover of C. Okay, let me adjust it. So, what is compact set? If a finite subcover of S is contained in each open cover, okay, if a finite subcover of S is contained in each open cover, or if and only if every open cover has a finite subcover, okay, you can consider this. If this is more precise statement, that if and only if every open cover has a finite subcover of a set, right? If and only if every open cover has a finite subcover of a set, then it's called compact set. Example, let S equal to A1, A2, dot, 8n is a finite subset of real numbers, okay? And G be the family of open cover of S. G be the family of open cover of S. Then there exists a open set containing AI belongs to S, okay? Then there exists a open set containing AI belongs to S. Therefore, S is finite. So open sets containing AI are also finite, right? If S is finite, because we have considered S as a finite, okay. So open set containing AI means what? AI means A1, A2, A3, A4, dot, n. Okay, so S is finite. So open sets containing AI are also finite. Therefore, G has a finite subcover of S. So we can say S is compact, because this is the definition of compact set. Now question. Prove that every closed subset of a compact topological space is compact. Okay, this is a question. These questions often come in university examination. These questions often come in university examination, and these are the type questions. Okay, so prove that every closed subset of a compact topological space is compact. Let Xt be a compact topological space and F be a closed subset of X. Then let C equal to G alpha be an open covering of F. Okay, then we can write this in the previous example. We see that we can write this, that F will be a subset union of G alpha. Okay, consequently we can write that X equal to F union X minus F, right? And that will be the subset of union of G alpha union of X minus F, right? Where X minus S is open, correct? Thus G alpha X minus S is an open covering of X, right? Thus G alpha comma X minus S, the set G alpha and X minus S is an open covering of X. Now let being compact. Now as X being compact, okay, now we have we have proved that it has been that we have to prove that every closed subset of a compact topological space is compact, okay, and we have considered that let Xt be a compact topological space, right? Then X will be compact. So X being compact and X minus F covering no part of F1, okay. So X being compact, X being compact, and X minus F covering no part of F, right? We have seen that X minus F is not covering any part of X minus F covering no part of F, right? X minus F covering no part of F. We have seen that. How we have seen that? Where, because this is open, right? This is open, and we have the union of F, union F X minus F, that is the subset of this, and that is the subset of the intersection of, sorry, union of all of G open sets, G open set of all the open set that belongs to G, right? All the open set that will be belonging to G. I mean, and also as well as the union of X minus F, right? So that, what does that mean? That means X minus F is not covering, not covering F. No part of F is covered by X minus F. Okay. It follows that if there exists finite number of indices, say alpha 1, alpha 2, alpha 3, and alpha n, right? If there exists a finite number of indices, say x alpha 1, alpha 2, alpha 3, alpha 1 means what? G1, alpha 2 means what? G2, like that, right? Such that if subset of G alpha y by I equal to 1 to n, okay, this shows that the open covering C of F is reducible to a finite covering, hence F is compact, right? This shows that the open covering C of F is reducible to a finite covering, hence F is compact. Now define, next question. Now define, okay, take a screenshot of the page. Take a screenshot of the page. I am giving you 1 minute to take the screenshot of the pages. This is screenshot are required because what I am explaining, you have to compare this with this screenshot, okay? Okay. Take the screenshot of this page also because I will be going through the questions. Okay, next question. Define local compactness and prove that every compact topological space is locally compact, but locally compact topological space need not be compact. Define local okay, because what I am making you understand here, if you want to understand, I have already told you, if you may not understand a single line if you not actually gone through the all of my previous videos. You will be able to understand everything if you have gone through my previous videos. Else, if you have some previous knowledge in topology, or if you have already gone through the books of topology, okay, then you can understand. Else, you have to go through the all the previous video. Even you have to, if you are not that if you don't have that much knowledge in a set, or if you had knowledge in very good knowledge in a set but you have forgotten, okay, we are human beings, so we can forget, right? So if you have forgotten that, please go to my set theory and check for once, watch for once. Everything will be brushed up, then come here, you will understand everything, as well as the previous video of topology, because in the previous videos I have given all the things like what is topological space, okay, what is topology, then intersection, union of topology, then what is the open set, what is the closed set, okay, what is the, how to determine the limit points, okay, and many things, okay. So go through all of these videos before going through this video, right? Will not understand anything if you don't have the knowledges, whatever I have explained in the previous video. Okay, so what is the question? Define local compactness and prove that every compact topological space is locally compact, but locally compact topological space need not be compact. Okay, so answer: a topological space xt is said to be locally compact if and only if every point in x has at least one neighborhood whose closure is compact. Okay, so what is closure, what is neighborhood, what is closure, what is neighborhood? If you want to understand, go to my previous video. I have made videos for just for what is closure, what is neighborhood, so that you can understand the question answer. So I am not going to explain you that what is neighborhood and what is closure in this video, right? That has been explained in the previous video. Okay, so go there if you don't understand what is closure and what is neighborhood. Okay, a topological space xt is said to be locally compact if and only if every point in x has at least one neighborhood whose closure is compact. Okay, let xt be a compact topological space. Let x, small x, belongs to capital X, then x is a neighborhood of x such that closure of x equal to x, okay, is compact. Closure of x equal to x is compact. If you don't have idea of closure, neighborhood, go to my previous videos, because you will not understand what I am saying here if you don't have the idea of closure, because these are all based on the properties of closure of a set. Okay, properties of closure of a set, properties of compactness of a set, right? So properties of neighborhood of a set. So if you don't have idea of that, what is neighborhood, what is compactness, what is closure of a set, then how will you understand this? Okay, so that is why I am asking you to go to previous videos to understand this. Okay, thus every point in x has at least one nbdx whose closure is compact, right? Hence we can say that xt is locally compact. We can say xt is locally compact. Take a screenshot of this. Okay, let me move to the next page. Let me adjust the paper. Okay, next, in order to show that a locally compact space need not be compact, consider the discrete space xt. Okay, now what is discrete space? I have given the definition in my previous videos. Go there and understand what is discrete space. So consider the discrete space xt where x is infinite. Okay, then the collection x belongs to x such that x belongs to x is an infinite open covering of x having no finite side covering. Okay, so xt is not compact. So xt is not compact, but xt is locally compact for if x belongs to x. Okay, then set x is an NBD of x such that a closure of set x will be equal to x. Okay, which being a finite set is compact. Which being a finite set is compact. So it is proved. So this is proved. Okay. So take a screenshot of this page also. Next, if every 2 points of a subset E of a topological space X are counted in some connected subset of E, then prove that E is a connected subset of X. Okay. So these are the questions which often come in university exam. Even it will give you better understanding of the subject. It is not like it's a suggestion, right? If you understand this, if you want to understand this, you have to go through all the basic things. So if you don't have understanding of basic things, you will not understand this, right? That is why I am giving you the example. This often come in university exam, as well as if you go through these examples, it will clear your basic. It will strengthen your basic. Okay. If every 2 points of a subset E of a topological space X are contained in some connected subset of E, then prove that E is a connected subset of X. Suppose E is not connected. Okay, when we are going to prove that, we will always consider the reverse. So I am considering the reverse. Suppose E is not connected. Then there exist two non-empty subsets G and H of X, such that G union closure of H equal to phi, and G closure of G union H equal to phi, and G union H equal to S, because since G is not equals to phi, H is not equal to phi. So if you do union of G, then we will get something that is S, right? So if you please go to my previous video and just see the what is the closure of the set, right? You will understand everything. Okay, let me adjust the paper. So there exists A. So there exists A and B. There exists A belongs to G and B belongs to H, and so A belongs to G and B belongs to H. Okay. So we can say that A and B are in connected subset of P of S. Okay. Let us suppose we are considering a subset P. Okay. Then if we have a subset P of S, now we can say like that because A belongs to G and B belongs to H, and A and B are, then what we can say that A or B will be present in connected subset P of S, connected subset P. Let us connected subset P in which A and B both are contained and which is a subset of S, right? So we can say that. So if A belongs to G and B belongs to H, okay, then we can say that A and B are contained in connected subset P of S. Okay. Now P is a subset of G union H, right? P is a subset of G union H. Obvious, it is obvious. And P, then what does it mean? It means either P belongs to G or P belongs to H. Either P belongs to G, P is a subset of G and P is a subset of H. Either P is a subset of G or P is a subset of H. Okay. And either AB belongs to G or AB belongs to H. Okay, P belongs to G or P belongs to H, and either AB belongs to G or AB belongs to H. Okay, let AB belongs to G. Okay, but previously we have assumed that B belongs to H, right? Let AB belongs to G, but what previously we have assumed? We have already assumed that B belongs to H. Okay, so we can say that G intersection H is not equal to phi, right? G intersection H is not equal to phi. Hence, E is connected subset of X. Proved? It's that simple. It's not very hard. Okay, take a screenshot of this. Take it a screenshot of this one, and then the next page. Okay. So I think you have taken the screenshot of this page and this page, and I guess this is the last question for the day I made for you. Let's check. A topological space XT is disconnected if and only if there exists a non-empty proper subset of X which is both closed and open. This is a very important question, often come in university exam. A topological space XT is disconnected if and only if there exists a non-empty proper subset of X which is both closed and open. Okay, let A be a non-empty proper subset of X which is both open and closed. What we are considering, let A be a non-empty proper subset of X which is both open and closed. Then A complement is a non-empty proper subset of X. non-empty proper subset of X. All of these things I have explained in my set theory and previous videos of topology. If you don't understand, go there. Everything will be easy, like everything will be very easy for you to understand if you just gone through those videos. Okay, I have already told you, because I am giving you here question and answer. I am not going to understand that what is the complement of a set, right? So let A be non-empty proper subset of X which is both open and closed. Then A complement is a non-empty proper subset of X which is both open and closed. That will be both open and closed because this is complement, right? And it belongs to X. So they have to be both open and closed. So we can say that A complement A phi always complement of two, always intersection of a set and complement will be phi. If you know the definition of complement, you will understand it, that why this is phi. Okay. Now closure of A is equal to A, and closure of A complement also will be here equal to A. Closure of A will be equal to A, and closure of, because we have already told you that subset of which both open and close. Okay, then complement will be open and close. Then what does that mean? That means that if we take closure of set A, it will be equal to set of A, and if we take closure of set A complement, that will be also equal to the complement of this set. Okay, so we can say that A complement, A closure union A complement equal to A intersection A complement. A closure intersection, I am also a human being. Sometimes I said wrong things, but I correct that instantly. So let us suppose A closure of A intersection A complement equal to A intersection A complement. Okay, this will be equal because in the previous page we have already seen that will be equal to phi. It always equal to phi. If you go to the definition of closure of a set and complement of a set, you will understand this is always phi. And A intersection or closure of A complement equal to A intersection A complement equal to phi. So what we are seeing here, that closure of A intersection A complement equal to A intersection A complement equal to phi, and A intersection closure of A complement equal to A intersection closure of A intersection A closure of A complement equal to A intersection A complement equal to phi. Also X equal to A union A complement. It always happens. If you know the definition of complement, it will understand that X will be always equal to A union A complement, because A will be the let us suppose X equal to 1 2 3 and A equal to 1 2, then AC will be 3. Then if you union A and AC, we will get 1 2 3. Okay, this is like that. So this is, thus X is the union of two non-empty separated sets, hence X is disconnected. So we have proved the question. So thank you for watching. Please subscribe my channel to get more questions on topology as well as abstract algebra, differential equation, complex analysis and real analysis, which often come in university examination, as well as those are the type questions. If you understand those, you will have very good basic knowledge in subject, so that each and every question you can solve of your own. Nothing is needed for that, and it is free. You don't have to pay anything for this. So please subscribe my channel to be notified. Okay.